In this video, we demonstrated how our L-AVI model runs on a high-resolution lunar image, performs patch-based inference, and generate scientifically validated reconstruction results. Okay, let's test our AI model L-AVI with its TRL-4 upgrade. This confirms we are testing the latest iteration of our model. Next, switch over to Visual Studio Code to ensure our environment is ready. In the Explorer pane on the left, we can verify the TRL-4 project files are loaded, including illumination_generator.py, dual_head_model.py, and our target script infer.py. Everything appears to be in place. Now, we are passing a specific test image, t-sample1.tif, located in the data/test subdirectory as an argument to the inference script. Press enter to run. Monitor the terminal output. The script initializes, indicating it is using device CPU. It then proceeds to loading image, revealing the image dimensions are quite large at 12,137 by 14,348 pixels. Due to this high resolution, the system notes it is running patch-based inference, processing the image in smaller sections to manage memory usage. Allow the process to complete. Once the patch-based inference finishes, the script moves to computing metrics downsampled. The final output displays the quality metrics for the reconstruction. A peak signal-to-noise ratio, PSNR, of 22.0815 decibels and a structural similarity index, SSIM, of 0.506009. Let's analyze the visual results. Open the generated histogram_comparison.png file. This chart displays the intensity distribution comparison. The blue histogram represents the original image data, while the orange represents the reconstructed data. We can observe a high pixel count concentration at the lower normalized intensity values on the left. Finally, return to File Explorer. You will see 4 files listed here. To start the analysis, locate and open the file named lunarsurface.png. Upon opening the image viewer, we are presented with a 6-panel grid displaying various analytical metrics for the lunar surface data. The mouse cursor initially hovers near the top row, which contains the grayscale reflectance, surface gradient magnitude, and micro-contrast map. Next, we scroll down or focus on the bottom row to review the shadow density map, the dust risk index shown in a heat map gradient, and the L-AVI reconstruction. The cursor hovers specifically over the dust risk index to verify the high-risk areas indicated in red. Zooming out slightly, observe the header of the report, which displays the overall quality metrics. A PSNR of 22.08 decibels and an SSIM of 0.5060. Having reviewed the summary panel, close this window or navigate to the next file. We now view reconstructed.png. This image shows the isolated reconstruction result labeled with the ID 139-21334 and overlaid with a coordinate grid. We briefly check the integrity of the surface features here. Returning to the file list in Explorer, now select and open the third file, scientific_comparison.png. This side-by-side view is critical for validation. On the left is the original lunar image, and on the right is the L-AVI reconstruction. Move your mouse over the original image on the left to compare the shadow details and crater definition against the reconstruction on the right. This confirms the algorithm's fidelity. In this experiment, the model successfully processed a 12,000 by 14,000, approximately 174 megapixel lunar surface image, demonstrating computational stability and scalability for large planetary datasets. The achieved PSNR of 22.08 decibels indicates moderate photometric reconstruction fidelity, confirming that the model has effectively learned global illumination patterns while still exhibiting minor loss of high-frequency surface details. The SSIM score of 0.506 reflects partial structural preservation, meaning macro-terrain geometry and major crater formations are retained, though micro-textural features such as regolith granularity and sharp crater edges remain somewhat smoothed. Gradient magnitude analysis clearly highlights topographic discontinuities and crater boundaries, validating structural sensitivity in the reconstructed output. The micro-contrast mapping reveals variations in surface texture, while shadow density analysis identifies illumination-dependent regions that may influence operational visibility. The derived dust risk index integrates local contrast reduction and shadow intensity, producing a spatial proxy map that could indicate potential regolith mobility zones or rover traction risk areas. Overall, the system demonstrates a TRL 4-level functional prototype with quantifiable reconstruction accuracy, structural retention capability, and preliminary lunar surface intelligence mapping, forming a strong foundation for further optimization toward engineering-grade deployment.